All right, so here's the FRQ practice I had from last week, which apparently all of you know exactly how to do, which is interesting because no one showed up for the session. So I will make a video, obviously, so you can check it. And if you're watching this video right now, good for you because there's some extra credit on it. All right, here we go. So that's the problem. I'm not going to read it all to you. Calculate the mass of the object. Okay, so you need to calculate the mass of the object. Well, I got velocity. How do I do that? I need like acceleration or something, or momentum. Oh yeah, the momentum before it goes to momentum afterwards, of course. So m times v equals m, which changes because it hits that block, times v. Well, wait, Mr. Cooper, what's that? That's the v right here, right? See, that's the v they gave you. Okay, well, wait, why is t equals 0? Because that's after the collision. But shouldn't it be like t equals 0.1? Well, how about this? Why not 0.01? Why not 0.001? Why not 0.0000000? Yeah, 0. It's right after the collision. And just so you know, 5 times 0 is 0, and 8 over 1 is 8. So we plug that all through, and we solve for that mass. You get 500 kilograms. Boom. Moving on. I'm going to go fast a little bit because obviously you all know how to do this, which is funny because these are some tough questions. Assuming an initial position of x equals 0, determine an expression for the position of the car object system after the collision as a function of time. Well, here we have a problem now. We have velocity. So how do we go from velocity to distance? Well, we're going to have to take the integration because dx over dt, which is speed, equals 8 over 1 plus 5t. So x equals the integral of 8 over 1 plus 5t dt. Okay, so we need to do some u substitution here to solve this. So u equals 1 plus 5t, which means dt is 1 over 5 du. Okay, no problem there. So x equals, and I'm going to pull out the 8/5, which would account for the 1 over 5 and the 8 that's already there. Integral of du over u. Well, what is the integral of 1 over u? Yeah, natural log 1 plus 5t. Plus c. Now be careful here. This c is sort of required if you wrote it like this, and that's needed there. Now, at t equals 0, tell me something. What's going on with my distance? Well, it's supposed to be 0. So then c also must equal 0, right? Because if your distance is 0, then you have 0, okay, 0. Boom. So our answer is 8 over 5 natural log 1 plus 5t. Moving on. Nice little integration there. All right, so there are two ways to do this one. For rotation, for a car object after the system collides as a function of time. So F equals ma. So we're trying to go from velocity, and we need, what do we need here? An expression for what? Expression for the resisting force on the car object system. So F equals ma, so m equals dv over dt. Okay, so wait. Don't we have a v? We do. So acceleration, right? That's dv dt. We know that. So dt, because that's the v right here, right? So that like takes care of this. So this equals this, which equals this. Yes, very good. Moving on. So what do we do? How do we go from velocity to acceleration? Well, we take the derivative. And the derivative of 8 over 1 plus 5t, because remember that basically is in the denominator, so it's to the negative 1, would be a negative 40 over 1 plus 5t squared. Wait, why is it 40? Yeah, that's a derivative. I'm not helping you with that one. Force equals 1,500 kilograms. We know that from our last one because 1,000 plus 500 times this, which is our acceleration. And force equals that as respect to t. Questions? No? Okay, moving on. And that should kind of make a little bit of sense. Your acceleration probably should be negative. It's slowing down, right? Okay, moving on. Now, the other way to do this could be F equals dp dt. Now, personally, if you thought of this way, that's impressive. I didn't. And what's dp? What is momentum? Well, it's mass times velocity. So, mass times dv dt. Wait a second. That looks an awful lot like that. It does, because they're the same thing. And from that point on, the problem's identical. Moving on. Determine the impulse derived from the car or the system from 0 to 2. All right, so impulse is the change in momentum, or the mass times the change in velocity. So impulse equals my mass, right, times the change in velocity, which would be the velocity at 2 seconds, minus the velocity at 1 second. And wait, why do you put a 1,500? Because that's the mistake I mentioned earlier in the video. There should be an equal sign there. But since I've been doing videos, and like the test video I just did took like 50 takes, I swear. And this video I think's on already like take 7. I'm not retyping it because I have to redo all the animation. So here's what you do. On remind, you go Foxtrot. There should be an equal sign there. And then you tell me what assignment name from Infinite Campus that I can change, because you notice there's stuff I can't change now. You want 2 points, and I'll add you 2 points. Moving on. It's only be the first couple people who told me that, but there should be an equal sign there. Sorry about that. So 15 times 8 over 11, right? That's that, was it 1 minus 5t or whatever it is? Yeah. Minus 8. Boom, boom, boom. 0, 8. Second, we're talking about that. Okay. Equals. There you go. Boom. There's another way to do this. So impulse also equals the integral of f dt. You could have done it that way. Or f average times dt. So integral from 0 to 2. Well, there's the force, right? That's the equation we got, and you just have to integrate that. And if you integrate that, you'll get this answer. Good luck with that one. Moving on. All right, here's our last question finally. Now, this question is kind of crazy because there's a bunch of ways to solve A and B. I'm going to show you some of what I think are the most obvious ones. There are even more. If you want to know about that, just text me a remind message, and I'll send you the answer key part that has the other ones, because I only did like 3 or 4 of them. There's like 8, I swear. Okay, so this approach for solving A and B is using translational and rotational dynamics. So sum of the forces equals ma times the center of mass. Okay, that makes sense. And torque equals I times alpha of the center of mass. Okay, so mg sine theta, right? That's going to be my mg sine theta minus force friction. Wait, how do you know there's friction? Because it's not slipping, right? So if it was slipping, it would be sliding down, but it's not, which means there has to be a force pushing it up. So that's why it's also minus force friction equals MACM, right? Okay, that's the MA part, right? Okay, moving on. Okay, so problem is force friction. How do we get rid of force friction? Well, we know force friction is the reason why we end up using torque, okay? That's why we use torque, to get rid of that force friction and make it a little bit more easy to understand. So alpha, okay, just remember alpha, the center of mass, is A, the center of mass over R. I know they look similar, but if you look close, you can see that little tail right there, which makes it an alpha. Let's just keep that in mind. So force friction times radius, that's going to be our torque, equals mr squared. And that mr squared came from the problem up here, mr squared. A, because it's mr squared alpha, right? Torque equals I alpha, which is A cm over R, okay? So remember, this wants, what does it want? Acceleration. That means it's talking about driving expression for acceleration, which is talking about of the center of mass as it rolls down the ramp. It's talking about linear here in a sense. So we kind of got to get rid of that alpha. That's going to be no good to us. So I can cancel some things out. There's an R in every term. So that cancels out, the squared cancels out, and technically that cancels out. Or you could say this cancels out with that, and then this cancels that out. Either way, all the R's are gone. So force friction equals MACM. It's that simple, because all the R's cancel out. You can figure it algebraically if you want. Okay, so now when I go back into this equation right here, which comes from this force equals MA, where I have force friction, I'm plugging in this. So mg sine theta minus MACM, that's the force friction, equals MA center of mass. Boom. Okay, I get you. And then you simply work it out and you get this. What? How do you do that? Algebra, I'm not helping you with that. If you need help, you can obviously shoot me a line, or maybe you should have showed up to the session. Moving on. All right, here we go. B, drive an expression for the speed of the center of mass of the hoop when it reaches the bottom of the ramp. Though the bottom of the ramp here, not here. So Vx squared equals V naught squared plus 2a delta x. All right, so I didn't say really final because it's not really final. This is equation number 5, just so we're clear. And delta x isn't exactly right because it's going down this ramp, right? Okay, so 0, V dot is 0. We know it starts at rest in a sense. So V squared equals 2, which is that 2a delta x, 2a, which is that. We figured that out already. That was that derivative from the velocity. L, okay, moving on. And boom, and there you go. Oh, L is that distance. Hey, Mr. Cooper, that looks kind of familiar. It does, and it should. Okay, moving on. Now, that was one way to solve it. Now, another way for part A, and you'd end up using the same thing for part A, you can also use torque about the point of contact between the hoop and the ramp and parallel axis theorem. So the last one we did where we solved part A, we used the center of mass, but you can use the point of contact. So in a sense, you're not rotating around the circle, everything is rotating around where the ramp, the hoop touches the ramp, and that makes it a little bit more different, okay? So torque equals I alpha center of mass, right? In this case, I, which is going to be the point of contact, right here, equals I center of mass plus MH. This is parallel axis theorem. This H can often be considered an R, but it's the distance from the center of mass to where you're rotating around. So in this case where we have a hoop, the distance from the center of mass to where it's rotating around, excuse me, is R. Okay, now why would you do that this way? Because in a sense, if you think about it in a free body diagram, it's constantly at rest because it's not slipping. So right here, that force normal is kind of negated by that fact. So what's going to happen is you're rotating, instead of rotating the center of mass, you're rotating around this point right here, which can make it a little bit different. It's kind of a neat way to solve it, but it's definitely a way I'd never think to do it myself. This was a way I found. I was like, oh, wow, that's kind of cool. So I equals mr squared plus mr squared. So the I of the point of contact right here, not the center of mass, is 2mr squared. Okay? Now again, to think about it, that's kind of like everything is at rest at that point of contact, right? Because there's no slippage, because it says that. Okay, moving on. So alpha equals a center of mass, so torque equals Rm g sine theta, right? Which Rm g sine theta equals 2mr squared. Okay, that's our I from the point of contact, ACM over R. That's why you can do this. So that force friction that would be involved in here is sort of negated by the fact that we're not rotating. We're going about this point. So the distance about this. So if you think about this, this is why this kind of gets rid of the force friction. As you go right here, force friction is mu force normal, right? So mu force. Yeah. So the force that goes right here, the distance from that force to the point of rotation, and we're saying it's rotating about this point right here, would be 0. That's why you don't have that force friction in there. That's why you use parallel axis theorem. It got rid of the force friction. Hopefully that makes sense. If it doesn't, hit up one of my Q&As. It's a really novel way to do it, I think. Ends up getting the same answer, obviously. Okay, so there we go. So that was kind of neat to get rid of the force friction that way, because either way, you know you got to get rid of that force friction, and the force friction is the torque of the force friction, right, is the force friction times the radius. Okay, well, the radius from the axis of rotation is 0 if you're doing it at the point of contact. Again, I hope I'm making sense there. All right, so approach for part A and B using conservation of energy and kinematics. So this way you have to work first, do for part B first, which is neat. So potential energy, all the energy equals, K rotational, I love K rot, or K translational, mgl sine theta, 1/2 mv squared, 1/2, yep, okay, boom, nothing crazy there. Okay, so omega equals V over R, mgl sine theta, yeah, looks like I kind of forgot to put an equal sign right there. Sorry, another little mistake. My apologies. Okay. Equals 1/2 mv squared, 1/2 mr squared. That's our I that we're given. And then V over R, that's our omega. So I do apologize. That should be an equal sign. Sorry about that. So m's cancel out. Boom, 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 right? You got GL sine theta equals 1/2 V squared. Okay. Plus 1/2 V squared equals V squared, huh? 1/2 V squared plus 1/2 V squared equals V squared, right? 1/2 of V squared plus a half equals a whole. And you're left with, again, V squared equals GL sine theta. How do you get rid of the square root? Squared. How do you get rid of the squared sine square root? Boom. This is potential energy, right? So my height right here is L sine theta, because remember, it wanted it in terms of, do I have an expression that reaches the bottom of the ramp, right? But this is the only thing you know. So that's mg, that's L sine theta, that's your height. And then this is GL sine theta, right? Because your m's canceled out, your m's canceled out, your r's, this r canceled out with that one. And it's a squared, so it's V squared basically over R squared, that cancels out. And you're left 1/2 V squared plus 1/2 V squared equals V squared. So basically V squared equals GL sine theta. Boom, boom. Okay. I know I went fast. A, same thing we basically did before. GL sine theta equals 2A center of mass L. Okay. G over 2. Moving on. C. Now, there are a bunch of other ways to solve them. Feel free to hit me up if you did it a different way. Derive the expression for the horizontal distance from the edge of the table to where the hoop lands on the floor. Now, remember, when this takes off, it only has velocity in the x direction. And then you need the time to fall down equation. So delta y equals gt squared over 2, right? So t equals, hey, look at that, it's the time to fall down equation. delta x equals vxt, right? Okay, so delta x equals GL sine theta. That's what we got for the v, if you remember. Right back here. Oh, that's acceleration. Oh, that's a. That's right. That's a. You had to do this one backwards, and that's b. Okay, there. There's t. Aha. Put them together. What have you got? Bippity boppity bippity boppity bippity boppity boo. Combine them. The g's cancel out, right? L delta y2 sine theta. There you go. Did you like that bippity boppity boo? I did. Moving on. Okay, so how will the distance from the edge of the table to where the disc lands on the floor compare with the distance determined by part C? What did part C ask you to figure out? Oh, the delta x. Okay, let's think about this, okay? So how will the distance from the edge of the table, so this distance from the edge of the table to where the disc lands on the floor compare with the distance determined by part C? So, I'm sorry, the distance from here to here, right? How will the distance from the edge of the table to where the disc lands on the floor compare with the distance determined in part C? Suppose the hoop is now replaced. All right, my brain's just stopped working. How will the distance from the edge of the table to where the disc lands on the floor compare with the distance determined in part C for the hoop? Sorry, guys. For some reason, my brain just stopped working. Okay, so basically I'm stupid. I didn't even reveal the question. Suppose the hoop is now replaced by a disc having the same mass m and radius r. How will the distance then? Okay, so let's talk about this. How is a hoop different than a disc? Well, if you think about it, if you remember, the hoop has all of its mass out on the radius, and the disc has its mass closer to the center, kind of influenced out. So is it going to have a higher I or a lower I? This would be the question you want to ask yourself here. And it's going to have a lower I here. Okay, so the disc has a lower I than the hoop. So the hoop has a higher I. What is that going to mean? Well, if it resists the inertia less, it's going to roll faster. So will the disc land far? Basically, what this is asking, will the disc land farther away, the same, or the distance? Well, if it's going to roll faster because it resists the change in motion less, then obviously it's going to be greater than. And what's my rationale? Well, the rotational inertia of the hoop is greater than the rotational inertia of the disc. If the disc is less, if the disc has less I, then the disc will have a greater speed at the bottom of the ramp. So if the Vx is greater, then the distance it traveled in the air would be greater. That kind of makes sense. All right. Hope that answers your questions. And I already did this one. Have a good day.